In this lesson, we're going to look at the difference quotient, figure out what it means, and how to use it. Finding the slope of a line is pretty easy. You've probably been learning about slope for years. Sometimes it's called rate of change. On a graph, you can find it by looking at the rise over run between 2 points. Sometimes you don't have a graph to look at, you're just given 2 points, so like x1, y1, and x2, y2. And you've probably learned that you can find the slope between those 2 points using this formula, so y2 minus y1 over x2 minus x1. But wait a second, isn't this a difference in a quotient? Sounds a lot like a difference quotient. So back to what the paragraph said. It says finding the slope of a line is pretty easy, but talking about the slope of something like a parabola is a bit more difficult. And since most things in life are more complicated than linear functions, it's important to have a way to determine slopes of these functions. Depending on where a point is located on a parabola, the rate of change will be different. We can, however, estimate the slope of a parabola at any point by grabbing 2 points and finding the slope between these points. The line through these 2 points is called a secant line. For example, if we look at this parabola, it's actually just the function x squared. But depending on where I'm at on the parabola, the slope is different. Like over here, the slope is negative, and over here the slope is positive, so it's always changing. If I wanted to know what the slope was at x equals 1, I could estimate it by first picking this point where x equals 1, and then looking at a point very close to it. So this is fairly close on the parabola, that's where x equals 2. And you can see if I connect those 2 points, it creates this blue line here. That's called the secant line. And you can see how it's not telling us exactly what the slope is because the parabola actually kind of cuts through the secant line and then comes back through it here. Ideally, I'd want a tangent line, which would just barely skim the parabola as it passes by. But for right now, I'll settle for the secant line because I can see how closely it's telling me the slope of the parabola. So let's actually do this. Let's find the slope of the secant line between these 2 points. The first one is 1, 1, and the other one is 2, 4. And if you think of like rise over run, well, the rise, that's just the difference in their y values, so 4 minus 1. And then run is just the difference in their x values, so 2 minus 1. And that, of course, just gives me 3 over 1, which is just 3. That means the slope of that secant line is 3. So that secant line is telling me roughly what the slope of the parabola is at that x value of 1, which on the parabola, that was the point 1, 1. That was pretty easy to do, but in practice, it's usually nice to be able to find the slope of a weird function at a lot of different points. So let's generalize this process so we can estimate the slope of some more complicated functions at many different points. So before I had those points labeled specifically, but now let's just label them generally. Like for this first point, let's just say it's some x value. It could be any x value. And since we're dealing with a specific function f of x, I'm going to call the y value, now this is weird, but it's whatever I'd get out of the function f of x when I plug in this x value. So this point is going to look like x comma f of x. That's kind of like saying the point x, y. It's just more specific since we know the name of the function is f. Now I also have to label the second point, and this is kind of the weird abstract part of all this. Imagine these 2 points getting closer and closer to each other on the parabola. What would happen is as the second point gets almost exactly to where the first point is, the secant line would basically become the tangent line. So we could say as the 2 points get closer, the secant becomes the tangent. So all of that to say, I want the second point to be really close to the first point, x. So stick with me, we're going to call this distance here h. What that allows me to do is that then I can call this point x plus h. Like if I start at this x value of x, and then I add h to it, then this x value is x plus h. And now I really have no idea what the y value is for this random point x plus a little bit plus this h. So I'm just going to call it f of x plus h. So one more time, just because all of this is so weird, I'm starting with some x value. If I add h to it, then this other point would be x plus h. If I plug this first x value into the original function f, my output or my y value would be f of x. So this first point is x comma f of x. And up here, if I plug this x value in, which I'm calling x plus h, if I plug that into the function f, I would get f of x plus h. So that would be my output or my y value. So this point is x plus h, comma, f of x plus h. So to fill out the notes, it says we'll call this first point x, comma, f of x, and then we'll move a little bit to the right, let's say just h units. That means the second point would be x plus h, comma, f of x plus h. So now let's use these 2 really generic looking points and let's find the slope between them. Well, up here when we found the slope, we did y2 minus y1. That would mean f of x plus h minus f of x. Because here's the second y value minus the first y value. So I wrote f of x plus h minus f of x. That's the numerator, and then we have to divide by x2 minus x1. Well, that means this x value minus this x value. So x plus h minus x. Now there isn't much simplifying I can do. The stuff in the numerator is stuck because this is just a bunch of function notation. But the stuff on the bottom is x minus x, well that goes away, and I'm left with just this. And that is officially your difference quotient, because here's your difference in a quotient. It's just a really fancy way of writing the slope. Now there are a few things we have to be careful of. H, for instance, cannot be equal to 0 because we're dividing by h. And that's really unfortunate because remember originally I wanted to take this point and move it closer to the first point, which means I wanted h to get really close to 0. So even though h can't be 0 exactly, we're going to be looking at the value of the difference quotient as h gets really close to 0. And that's what the notes say here. Ideally, the value of h would be so small it would basically be 0, so that our slope is as accurate as possible. Actually, if h equals 0, that would be best because then our secant line would become the tangent line. So we can't use h equals 0 because we can't divide by 0 in the difference quotient. So let's look at another example now. We're given this function f of x equals x squared minus x, which looks like this parabola here. And I want to find the slope of it at x equals 2. And I'm going to be picking a couple smaller values for h. So we're not exactly using the difference quotient here, we're still just kind of looking at an easy application. So here's the point on the parabola where x equals 2. I want to estimate its slope. And I see there's another point on the parabola here, and that's 1 unit to the right. That's like saying h equals 1, so that's this first example. I'm just going to quickly find the slope by looking at the rise over run, which is 4 over 1. Now, if I were to draw a straight line through these 2 points, the parabola is actually kind of inside this triangle. It looks like it actually has somewhat smaller of a slope than 4. So let's see what happens if I plug in a smaller h value. Like, instead of going 1 unit to the right, what if I just went half a unit to the right? If you follow that up to the parabola, it looks like it's not exactly 2 units higher. So let's figure out what that point is, and we can do that because we have the function here, f of x. So the first point was 2, 2, that was on the parabola already. That was an easy point right on the grid lines. But the second point, that has an x value of 2.5 because I'm moving 0.5 units to the right. So it's 2.5 comma, and now I just have to plug 2.5 into this function. And when you do that, you get 3.75. So that's the y value, and in fact that is a little bit less than 4, just like I saw over here on the graph. So now when I find the slope between these 2 points, it would just be the second y value minus the first, so 3.75 minus 2, over, and then subtract the 2 x values, so 2.5 minus 2. That gives me 1.75 over 0.5, which is the same thing as 3.5. Now that's not much of a difference, but you can see that depending on which h value I pick, the slope does actually change a little bit. So the question then becomes, how small of an h value do you think you should pick in order to pick a slope that's accurate enough? So let's explore that by evaluating the actual difference quotient for this function, x squared minus x. So the first thing that it tells us to do is take x plus h and plug that into the function. That means I have to plug it into both of these places for x. So that means x plus h squared minus x plus h. Then it tells me to subtract the original function f of x, and since there's 2 terms in the function, I'm going to put them in brackets here, x squared minus x. That'll just help me keep them grouped together. And then the whole thing is over h. Since this is a binomial squared, I'm going to use a box to expand that over here. So that gave me x squared plus, and then 2xh terms, and h squared. Now I have to distribute this negative into these parentheses. That would give me minus x minus h, and then distribute the negative into these brackets, leaving me with negative x squared plus x. This whole thing is still over h, and it seems like we've made things worse now, but we do have a minus x and a plus x, those cancel, and we also have an x squared and a minus x squared which cancel. So now I have h squared plus 2xh minus h. All of that is over h, and I encourage you to write that at every step because it helps you see that we're grouping this as one step of the problem. So now every one of these terms has an h in it, and I can't combine any like terms, but I could factor an h out of every one of those terms. So if I pulled an h out front, that would leave me with h plus 2x, and then don't forget the minus 1 from this last term. All of that again is over h, and finally I can cancel this out, leaving me with just h plus 2x minus 1. And that is your difference quotient for that function x squared minus x. What this means is it's just this very generic expression that depends on h and x. Now, what this difference quotient does, remember it tells me the slope of this parabola at any point x, and it also depends on what value h that I use. Now, what we might want to do is find the slope of this parabola at a couple different points, so like maybe -2, 0, and +2. And we might also want to see if changing h to like 0.1 makes it any more accurate than 0.5, or maybe we should go even smaller. That's a lot of evaluating to do, but what's really cool is if you plug this into Desmos, it'll actually allow you to evaluate something in two variables. So you can type into Desmos f of x comma h equals h plus 2x minus 1. And this is saying to Desmos that this is some function that has two inputs, x and h, and this is what you should do. You should add h plus 2x minus 1. So for instance, if I plugged in f of -2 comma 0.5, I get -4.5. So Desmos knows that x is -2 and h is 0.5. So this allows you to evaluate a bunch of different x and h values really fast. So when we fill these into the table, you can see the difference. Like if we use a more accurate h value, here when we used an h value of 0.5, so just a half a unit, we thought that the slope of the secant line was -4.5. But if you change that h value to 0.1, so a much smaller difference, now the slope changes to be -4.9. So you could say at the x value of -2, the slope is roughly -4.9. And if you use the smaller h value, you'd be able to find the slope even more accurately than -4.9. As a matter of fact, if you took this difference quotient and just thought of h being basically 0, and then just plugging -2 in, this would be 2 times -2, which is -4, minus 1, which is -5. So the slope at that point is basically -5 if you had an h value that was basically 0. So since the slope is really about -5 and we got -4.9 here, I'm thinking, yeah, that feels pretty accurate. Again, at an x value of 0, we found that the slope was about -0.9 when we plugged in the small h value of 0.1. So you could say at x equals 0, the slope is roughly -0.9. If you look at the actual difference quotient and plugged in about 0 for h and exactly 0 for x, this would all cancel out and you'd be left with just -1. So this difference quotient is estimating the actual slope pretty well. And again, you could say at x equals 2, the slope is roughly 3.1. And that should be enough about the difference quotient to get you started on some example problems.